We're now live on the internets. Give me 2 minutes, 3 minutes to finish welcoming people, and then we will get started. So I need to grab some pizza too, and dispel any confusion about the Zigrith meetup.
Does the committee know your channels?
What's that?
Does the committee channels?
Johnny, is that like a...
You just mean as in like in those MPSC channel?
Yes.
So it's not like a built-in language construct, but they standardize or needed.
So who's here for Rust? That should be 100% of people should be here for Rust. Who's also here for Zig? Sure. No way. All right, cool. Well, we're not going to have any Zig presentation tonight. It's just meet and greet. And we're going to start with a presentation in January that's on, I don't remember what the topic's going to be, but somebody in the Zig Discord, the Zig Utah Discord was volunteered. Tonight for Russ, we've got, it's still showing the wrong thing on the title screen. Let's switch that. There we go. We've got Herbert Wolverson here to talk about sending data with channels. So I'm just going to do a little bit of double checking that everything's going through. In fact, I see one thing that is not going through right now, which is that we do not have his audio captured here. So I'm just going to add a quick audio capture. Audio output capture. This is going to be browser. Okay. And then we're going to select, oh no. Well, that's not good. Oh no, please don't install the update. No. No. Oh, garbage. Okay, I'm going to try one other thing then. I promise, I got here early to get all this sorted out, but you know how it goes.
That's all right. I'm trying to filter out a singing concert in the background. So.
Okay, now output goes to the speaker's input from the cable.
While we're waiting, does anybody have any good stories? That aren't like 30 minutes, but more like 3 minutes.
Property.
But they have like a good ending.
Any story?
Like something that recently happened.
Okay, can you hear me now? Nod your head if you can hear me. Okay, but I
can
can't hear you now. Dang it.
Can you hear me? As I'm talking right now.
Oh, I know what to do here. I know how to fix it. I can fix it.
Maybe a little while ago, doing research into putting the Lisp language.
All right. Now speak again.
Can you hear me now?
That didn't
hello.
work. I'll try something else.
Did you recently graduate? Did you recently graduate from you?
Apparently, I need to set one more thing. I haven't hosted the Rust meetup in a long time, so
you came here.
my setup is a little out of date with the configuration of my computer and my operating system updates and such.
Yeah, I
Okay,
don't know
so
who Jay is.
monitoring
Before you
hear
output.
about
Where does my monitor output go?
Gotcha. Okay.
Yeah.
Audio.
For anybody who knows, you know.
Let's see.
Yeah.
Monitoring device.
They're hiring a lot of juniors.
Okay,
that have
speak
5
again?
years experience.
Hello.
Yay! All right, everything's making the full loop again. So we can see you on the screen. We can see you on the stream.
Yay.
We can hear you in the real world, and we can hear you on the stream.
Sounds
Huzzah.
good. How's my volume level?
I think that your volume level is good. If you want to boost it,
I am deaf as a post, so I never have the faintest idea.
all right, deaf as a post. Good. We like deaf posts around here. Okay, so now I will do the official welcome and start. Okay, so everybody, hello, welcome. I am AJ O'Neill. I am the former Rust organizer. I have been tempted by the light side. I've become a Zig Jedi, or a Zig Padawan, on the path to Jedi, as soon as TLS is implemented. And I am also starting the Zig meetup. Nathan's been doing the Rust meetup this whole year, but he had a scheduling conflict with family stuff, Christmas, so he had to ditch out because that came up. So I will be your talking head. Actually, I will be completely unimportant tonight. We also have we don't have Jeff in the room, but we've got remember your name again?
I'm Taylor.
Taylor. Okay, so we'll take all the accolades that Jeff deserves and we'll throw them at Taylor because he's an employee of Vivint. So many thanks to Taylor for being proxy for Jeff and Vivint for hosting us with a location and with food and with internet, everything that the body needs to grow and thrive. And let's see. We won't do introductions tonight because we're starting late, but we could just say names. We can just go around and say names. So I'm AJ, you are?
I'm Kimberly.
Kimberly.
Taylor.
Nigel.
Leroy's.
Leroy's?
Mm-hmm.
Robert.
Lewis.
Nathan.
Andrew.
Matthew. Alfie.
Also Andrew.
Also Andrew.
Don't break the.
And Spencer. Okay.
It'll be Andrew. You broke.
All right. So, and the people that are most interested in Zig, you are under no obligation to stay in this room. We can go skip and be in the other room, but I figured it'll be cool stuff to learn from Rust and similar communities. With that all out of the way, thank you so much for putting up with this delay, Herbert. Go ahead and introduce yourself and take it away.
Hi, hopefully you can all hear me. I am Herbert Wolverson. I'm going to be talking to you today about sending data between threads and async processes in Rust with channels. There's a couple of URLs up on the screen that I hope somebody can note down and share with you guys there. The GitHub link has the entire presentation and all of the code that I'll be referencing. And the VF nightly is just the link that I'm using to actually display the presentation. It's written in MD book, one of the standard Rust documentation. All right, so who on earth am I? My name is Herbert Wolverson. I currently live in Columbia, Missouri, but I'm originally from just south of London, England. I've been developing software for more than 20 years, so hopefully I'm older than I look, but you can't tell. Started with basic Pascal, C++. Eventually I got so sick of C++ after working on an Unreal Engine game, and finally shipping it that I desperately wanted to see what cool kids were doing, so I tried out Rust. And all of a sudden I really liked Rust, and then I released a site called the Rust Roguelike Tutorial, which is 83 chapters of free building a game in Rust. Kind of crazy. That turned into a book deal, and Rust came out, and then Rust brand teasers. Being going around talking to pretty much anybody who will listen to me, because I love doing this stuff and enjoy things like RustCon. I've just started working with a company called Ardan Labs, and I actually now teach Rust for a living. I'm also on a bunch of open source projects, including LibreOS, which is a Rust-based system that can do real-time traffic shaping for 20,000 customers at a time on one server for internet providers. It's pretty cutting edge stuff, so I learned a lot doing it, and I love doing it. So I'm excited to talk to you guys. I know there's a lot of Zig interest there. I've done a lot of Zig. I do talk to Go developers every single day thanks to Ardan Labs. So I'll mention Go quite a few times. I'm not trying to persuade you to go and use it. In fact, between you and me, I'd advise you to run the other way. But it's you okay?
Walk carefully because I was also interim leader of the Go meetup. Actually, that's not true, but I do love Go. I absolutely love Go, and
I like Go. I think that Russ is busy trying to eat a lot of Go's lunch. Because we joke a lot because everybody else I work with is a Go developer at Ardan Labs. I am the Rust guy, and so I'd say half my first break consisted of why should I work on Rust? And so that's what inspired this talk. We're going to look at one of Go's stunning central features and just how well Rust has implemented that. And how, if you are used to working in Go, you can quite easily transition over, take advantage of almost exactly the same thing, and benefit from it. What we're going to talk about is channels. Now, Go didn't invent channels. Channels seemed to originate around 2006 when Ben Jacobson, Linux fame and Unix fame before that, was looking for ways to move data between threads inside a real-time Unix kernel. And he wanted to do it in a way that didn't cause one end or the other end to necessarily lock up and block all data that's moving through the computer. So he was interested in a block-free approach. And he came up with the idea of a blob of memory that one half is writing to the head, one half is writing to the tail. And if you're really lucky, then the head never grows faster than the tail and your data gets through. So it evolved quite a lot from that and turned into something that doesn't crash your computer on a good day. And Go really became the central point to advertise channels as a concept, because Go is built all around the idea of Go routines, which are basically async tasks that hop between CPU cores, run in multiple threads, multiple tasks. And because it's so easy to spawn off a Go function and say, I've got this data, but I need to give this data to another function so I can have a pipeline of data flowing through. Go pretty much automated it, pretty much perfected the technology. It got it really, really fast. So you can easily send 15 to 20 million messages a second on a decent sized server without bringing the server to its knees and still have CPU time to do something else. You're almost limited by memory bandwidth. That's pretty cool. And so when you look at how Go did this, you have to understand how Go is set up. Go is a lot like Erlang in the sense that you have one thread per CPU core. That thread has a big list of jobs that are going to be running. In the event that a job is taking too long, another thread another CPU core that doesn't have anything to do can reach over into another core's list, grab that work, steal it, do the job. And so this is called green threading and is at the core of how Go made channels work so well. But the Rust guy, Rust started out without proper async. Some might say it still hasn't caught up, but it's getting there. But Go really proved that channels are a great way to make your threads talk to each other without having to tie yourself in a giant knot. And so Rust's fearless concurrency builds channels right into the infrastructure. And then the crate system provides tons and tons of more interesting ones. The Rust standard library ships with threaded multi-producer single consumer, so you can have as many tasks generating messages as you want, all going to one place. They all get stored in one location, and the sender doesn't have to block. So you send the message, you carry on going, you don't have to pause. And we're going to be taking a good long look at how that actually works in practice. And then towards the end, we're going to take a look at how Rust has almost implemented its own Go with Takio by implementing, and this should sound familiar, one thread per core, each of which has a task list, can steal work from other cores. It's almost exactly the same thing. Go has a few tricks up its sleeves that make it a little easier to work with, but Rust is getting there and it's catching up. Okay, so I've worded on enough. Let's have a look at some code. I'm going to assume that since you're a Rust user group, quite a few of you have at least got as far as making a thread at some point. If I'm wrong, feel free to shout and I'll slow down and start explaining things a bit more. But this is a very basic program. So from the standard library, we pull in thread just so that we don't have to type SDE thread all the time. We use thread spawn, and we're just going to print hello from a thread. And then in the main thread, hello from the main thread. And then when you spawn a thread, it gives you a join handle, which represents your interface for interacting with that thread you've created. In this case, we're just going to join it, which means we're going to wait for it to finish. And so I will activate the Rust Playground link. Is that enough or more? All right. Excellent. Okay, so this is probably this is basically the hello world of Rust threads. We've got spawn a thread. Inside the thread, we run this little closure that prints hello from a thread. Main thread prints hello from the main thread. We wait for the other thread. And it's going to be kind of random which one of these finishes first. In this case, the main thread and then the thread. Makes sense. It takes a moment to start the thread up, but just occasionally it goes the other way around. So what if you want to tell the thread to do something? Now, if you go back to old school C from the days when I was getting started, the way you usually did it was that you came up with a shared variable. In this case, I've got a message. I'm wrapping it in a mutex, and what a mutex does is it prevents concurrent access. So anybody who wants to access it has to lock it. If it's already locked, your thread just sits and waits until such time as the mutex lets you back in. We're putting an option, so there might be something there. If there is something there, it's going to be a string. And the other popular way is with atomics. So an atomic is a variable that can be changed, and the CPU provides some guarantees that it's going to change in one go. And so you end up very quickly with a really messy program. So we're making a new thread. Inside that thread, we're locking the message. So we're gaining exclusive access to it. We're looking to see if there is a message. If there is, we print it and empty the message. Then we have a look to see have we received a message that we should be quitting. If we have, we stop the loop. And then in the main loop, 5 times, we lock the mutex. We stick a message inside there where we'll just say hello 1 to 5. We'll sleep a little bit to make sure that there's time for the thread to actually do something. We'll store that we're quitting, and then we'll wait for the thread to quit. And so if I run this, the Rust Playground will compile and run my code. And you see, it does what you'd expect. It sends 5 messages. But that is a lot of code for something as simple as that. And if you start dealing with a truly big program, you are going to have a massive mess on your hand. And because you're going to need to start storing locked global variables or locked shared variables that are in scope for all of the threads that you want to control. And you've got just a potential for absolute spaghetti soup. And Rust, being a beloved programming language, tries its very best not to subject you to spaghetti soup, even though that is my daughter's favorite right now. All right, so how does a channel simplify that? Well, like I said in the introduction, a channel is a means of sending data from point A to point B. And it also makes your program more efficient in this case. And so right there in the standard library built in, you have standard library sync for MPSC, which is multi-producer single consumer. It's the default channel type in the standard library. So you can have as many senders as you want and one receiver. So everybody can talk and they all go to one guy, which sounds like every office I've worked in. And we are going to send a string. And so once again, we spawn a thread. I'm using move. I'm actually moving the receiver out of the main thread and into the thread that's going to use it. That's pretty normal for Rust concurrency. In the thread, I'm looping, and loop runs forever. And I call on the receiver, dot receive. And in this case, I'm just unwrapping. So if something went horribly wrong, my thread is just going to crash. Normally, you wouldn't want to do that. You'd actually want to check that the error means something useful. If I get a message, I print I received the message. If the message is the word quit, then I stop the loop and I stop. So 10 times I create message number in the main thread. With the sender, I send it into the thread, send quit, and join. So we run that, and 10 messages. Now, there's a couple of things in here that the eagle-eyed amongst you may have spotted. I'm not sleeping. That's because there's no contention on a mutex with the main thread locking it continually to see if there's something there. Channels are really smart and will actually inform the kernel that they're in a waiting state until they're notified that there is some data there. So your CPU in the thread isn't spinning, it's not pounding your CPU at 100%. Any reasonably modern kernel, it's pounding your CPU at 0% until a notify variable goes off, which the kernel handles for you, wakes you up, and tells you there's something to do. So you've instantly stopped heating up data centers, and you're not having to worry about locks. You don't have to worry about global variables. You've got a simple point A to point B message sending system. And in this case, I'm just watching for the word quit to quit. And so that's an improvement already over the old classic way of doing things with having a locked mutex variable. But this is Rust. Rust is all about using algebraic data types and similar to try and make it much more obvious what's going on, give you a more ergonomic experience. And you don't have to send strings through a channel. In fact, you can send anything through a channel so long as it is safe to do so, and Rust will enforce that safety for you. We'll talk about that a little more in a moment. So in this case, I've created an enumeration, and it's called command. The first option is print, send a string. The second option is quit. And then the program is basically the same. So we create the channel, but instead of creating a channel typed on string, we create a channel typed on the command we've created. And now we receive a message. We can just match on it. If it's an instruction to print, we print something. If it's an instruction to quit, we quit. It could be anything you want. So if you want to have just worker threads sitting in the background waiting for instructions, channels let you do that very easily. You can set up an enumeration, send them the instructions you want. You can even send them a sender to a channel that you have if you want them to reply back. And so this is the same program. It's just arranged to be a little more ergonomic, a little easier to read. It does the same thing, as you can see. Okay, did that make sense to everybody before I start diving in deeper? Awesome. All right. Now, channels are a lot of fun, and if you start writing complicated programs, you start getting into a little bit of what I call channel soup, which is after a while, it seems like you have a channel talking to everything and everything else, and you start diving onto cargo and crates.io, and there's a ton of different channel types out there, like a broadcast channel for sending one thing to everyone who's received that channel. That's awesome for telling people to quit. There are channels that automatically give you a way to reply back. There are channels that self-destruct after one message. You can do all manner of things with them. In this case, let's have a look at the multi-sender capability. And so this is once again, we're using the same enumeration. We're creating a channel just like we did before with command. This time I'm making a vector of join handles because I'm going to spawn several threads. I'm going to store all of the join handles just so that we can remember to wait for them at the end. And so senders are designed to be cloned. They're like an arc. When you clone it, it's still connected to the same channel. Just now you have your own unique sending point for posting data into the channel. And so we're going to count from 0 to 9, create our very own sender, make a thread that will, in that thread, we will send 10 messages, labeling which thread it is and what the message is. And because we've cloned my sender, when we move it in here, that thread has its own unique instance as a sender, so you don't have to worry about the borrow checker sharing mutably, all of that pain. It's designed to be cloned, it's designed to be sent all over the place. And then we just store the thread handle. We're going to make one more thread that is exactly the same as it was before. It receives the messages, prints whatever message it receives, and eventually quits. And finally, we'll add a quit message to the back of the queue. And then we'll just wait for every thread to finish. And so we've added only a few lines of code, and that worked earlier today. All right, I'll look at that in a sec. I'll look at that in one moment. But I just realized I didn't enable editing on this document. So I'm going to pull this to the side. I mean, what I did there was I panicked on line 21, but what I'm looking for is which program this is. Here it is. That's all right. I'm just embarrassed because I actually tested all of these yesterday. And then I updated REST. All right. Okay, I just had to change that last line there because I am unwrapping and actually got an error from one of my threads, but now you can see exactly what it's meant to do. So the issue was that I sent my quit message too early and the thread bailed out before I should have added a wait. But you can see that each of the threads spamming messages into the channel. It's relatively ergonomic in terms of you just need the one sender that you clone, you put it into your threads for sending. So if you have a pattern where you, for example, have lots of workers going on and you want them to send results to one place to do something with them, like log them or send them off somewhere else, this is a great pattern to use because you almost completely get rid of the need to worry about having some shared state. You just have a way to send the message out of the worker thread. And here we have 10 worker threads and into one receiver thread. If you're working in multiple teams, it's a great way to break your workload up and not have to worry too much about, how are we generating these results? That's somebody else's problem. All right, I wanted to highlight this because this is, in my opinion, some of the ugliest Rust syntax you can possibly get. Really hope Zig looks nicer than this.
One second,
sure.
We had a question in chat. RT asks, is a thread ever going to execute on a different core, or is it possible to always be on the same core?
Okay, so that is unfortunately operating system dependent. By default, threads will move between cores based on whatever the kernel scheduler feels like at the time. On Linux, at least, they're not likely to move on their own very often, but they will move if, for example, something else is really occupying that core and another core is empty. There's a crate called Core Affinity that I use quite a bit in networking code because it allows you to issue a one-liner to say this thread must always be on this CPU core and takes care of the abstraction because there's different system calls for that on Windows, Mac, Linux, and just about everything else. So it takes care of figuring out the underlying operating system call that says pin this thread. And once you've done that, you can be absolutely sure that if you've pinned to CPU 2, it's never going to leave CPU 2. Did that answer the question?
Yeah, we got a thank you on that.
Awesome. Sorry, I can't hear the audience. So, all right. So a moment ago, we just looked at how you can use lots of senders to create data going into one place. And we've looked at how you can use enumerations to send commands, in this case, just telling it to print something. So what about if I wanted to send a function? And that sounds kind of crazy, but you can do it. So using box, which is a smart pointer type, which means the contents of the box will be on the heap. So you're not actually sending the contents of the box, you're sending a pointer to the box. Using the infamous dyn dynamic tag, meaning that the exact signature of what's inside doesn't have to be exactly the same every time, and the size of the type can be figured out at runtime. It has to be something that allows to be sent between threads. Static, which is basically the keyword you use when you tell Rust that I really don't want to think about lifetimes right now. That's pretty much what static does, is you're saying that I promise you, I pinky swear that whatever I'm sending will still be there later. And so you probably ought to obey that, but gives you a little opt-out. FN once is a built-in Rust type for a function that isn't designed to send data back somewhere else. And in this case, we're going to specify that it has a parameter of an I32 and returns an I32. So with that in command, you can still create a channel with a command inside. You can then make your join handles just like we did before, spawn your threads, and when you receive execute, where unwrapping the function is f, we call let result equals f at 10. So when it receives the function, it will run that function with the parameter 10 and print whatever comes back. And so down here, and so we've only created the one thread, but into the thread, we use box new to create a new smart pointer and then put a function inside. So the first time we're going to send a function that just adds 1. The second time we're putting a function in that doubles it. Then we're telling it to quit. And that is kind of insane. And hopefully it doesn't have the same update problem. Nope, it works. And so the secret here is that this is how Rayon and other really advanced libraries build a thread pool. And you can do it yourself in 20 lines of code. You can build a system that allows you to pass a pointer to a function and have that other thread run the function. And so now imagine that you're building a giant data center size compute core. You've got the ability to have an enormous number of threads sitting waiting for something to do. And what's effectively a Lambda function, a closure, or it can be a bound function, anything you want, gets sent to that to work. All you have to do is add a reply channel to send the reply back, because you probably don't want to just put it on the screen. But in just a handful of lines of code, you've built yourself a flexible compute core with a thread pool. And so that's a relatively primitive, I think I just heard a chat sound. Was that you guys? Okay. Oh, okay.
Yeah, let's see. Can we go back to the other example, where I guess wherever the one where you're passing in a function is inside of a box.
Yep.
Uh, why do you need to tell it that it has a static lifetime here? Does the box not own the function?
The box does own it. I honestly was wondering the same thing as you, because it would not compile without that. And the conclusion I came to was that the Rust lifetime checker is unable to determine exactly when the box will cease to exist, unless you also wrap it in an arc, because the arc can be used to guarantee that it will stick around. I didn't use an arc, so the box will go away as soon as it's out of scope. And it seemed like the Rust lifetime checker was just giving up on trying to figure out when that would expire in a multi-threaded context. Does that make sense?
Okay.
I wasn't too happy needing a static there either.
Just a mysterious thing. That's all right. So it goes.
It is. And I dug into it, gave it about 30 minutes, and concluded that everybody else is saying it's static here, but nobody says why, so I'm probably as in the dark as everybody else.
Well, the compiler tells you what to do, you do it.
Yes, sadly.
Yeah.
I don't know, but kind of my guess is that saying that the function, you have a static lifetime for the function itself.
That would make sense.
And then essentially you're saying this function is living in a static lifetime and not like, I don't know, again, yeah, you're not getting, yeah.
One thing using static there does prevent variable capture, which would turn your program into total spaghetti. So if you had a closure that captured a variable main function, and then you send that function elsewhere, trying to justify that as being safe would be really tricky, because you can't ever really know what state the sender function is in. So that would actually make sense. Yeah, the function itself has to retain a static lifetime, so it can't be reliant on the sender still being around. All right. Any other questions? All right. So we covered the example of using receive, where you set a new block until such time as a message arrives. That isn't so great if you have more than one channel that might be sending you messages, or if you want to be doing something else and just occasionally checking to see if you've got a message. You might have a thread that's running a long-running calculation and want to check occasionally if you've been told to stop. So receive can also be replaced with receive timeout. In this case, and then you specify how long you want to wait to see if a message shows up. If you specify 0, it continues right away, unless there's a message. But this gives you the opportunity, for example, to have, here's two channels. The first one, I'm just sending the unit type, so I'm not sending a message at all, I'm just indicating that there is a message. And the second one, I'm sending a string. And so here we can call it receiver with the receiver for each of the two queues. So we check the print with a timeout to see if there's a message. And we'll do try receive, which is the other way of doing this, is an instant. There's no timeout. It's just carry on if you don't have anything to tell me. Otherwise, you return OK with a message. And so I just included that for you. So if you start wanting to get clever with threads, gives you a couple of different ways to pull threads if you don't want to just sit and wait forever. It's still more ergonomic than checking shared variables most of the time, but as you can see, the complexity starts to ramp up. It starts to get a little soupy. So again, you need to be careful when you start doing this too much. And the eternal question. Everybody who's into Rust, and I'm told Zig, starts worrying about performance. And so I worried about that too, because I was working on a program recently that is reading data off of a network card at about 10 gigs a second. And quite a lot of those packets actually trigger a message to other parts of the program for more processing. Specifically, we look at TCP packets, we look at the SYN and ACK counters, and measure the time between request for some data coming out and the data coming back in to give round trip time, letting us graph ISP performance in real time as perceived by the user. So if they're watching a video, you can tell exactly how long each chunk of that video has taken to arrive and get on their screen. And so I was sending a lot of messages, starting to run into issues with multiple million messages a second not really being enough. So I started digging in, looking to see how much better this could be. So I put together a relatively simple program. You should recognize most of this. We've got the same enumeration, the same channel, but I'm just going to time how long it takes to send messages. And on my computer, as opposed to the Rust playground, which gives me a different answer every time because it's a function of how many other people are using it, on average, my program has to wait 81 nanoseconds to send a short enumeration message to another thread. That is a fantastically small amount of time to have to wait. Now, it's not linear. For some reason, I got one message that delivered in 24 that was sent in 24 nanoseconds. We're not looking at delivery time, just how long it takes to actually send the message. So how long does your thread have to not do something else that's useful to communicate with a different thread? But also the very first one I sent took 1700 nanoseconds, which is massively longer than everything else. And so doing some digging, I discovered that channels actually have a vector inside them and allocate the first time you send a message. And if they back up too much with too many messages, they allocate some more. And so what you want to do if you're using a regular old channel is have a warm-up message at the beginning just to make sure that there is some space in that channel's buffer because it doesn't allocate until the first message. The obvious solution to that seemed like it would be bounded channels, which is with a normal channel, if it, okay.
So earlier you were talking about storing something on the heap and using that to send it over. Are you saying that there are two methods that channels use to get their data across?
Yeah, so the channel itself has a small amount of memory to buffer the data that's going from point A to point B, because it's not guaranteed that you will receive it at the exact instant that it arrives. And so what we're benchmarking here is how long it takes to get that data into the buffer. And it turns out that the buffer allocates lazily. And so the first message ends up taking 100 times longer than the second message because the first message allocates some space on the heap, the second just uses it, if that makes sense. And so I thought bounded channels sound like the answer, because a normal channel, if you don't receive anything, so you're sending into it and never polling the receiver, it will keep growing and growing and growing until you run out of memory and the kernel kills you. That's not ideal, not something you want to do in production. And it also sounded like, well, if it's lazily allocating, maybe that's the cause of the problem. So you can, built into the standard library also is a type called sync channel. It's basically the same thing, but it's more synchronous in the sense that you have an exactly bounded space in memory. That's where the messages go. In the event that you try to send a message and there's no room, the sender actually sits and waits unless you use the try type that just gives you an error. And so I tried that because that sounds like a solution to the problem. And what I found was my average speed was substantially faster, and that's because it's maintaining the buffer. But my first send was even worse because the sync channel still makes the terrible mistake of not allocating until there's something to allocate. And it allocates the whole buffer on the first message. And then everything is nice and super fast. And so once again, stuck with needing to send a warm-up. And so I thought, okay, well, maybe I can make it a really, really small channel. And it turns out that was a terrible idea because my average sending time went all the way up to 3,000 because my threads are not in perfect lockstep. And so my sender is spending quite a lot of time just waiting to see if I'm allowed to send yet. And so in other words, bounded channels are great, but you've still got the problem of warming it up. You've still got to, and now instead of having an unbounded channel that will grow, you do need to spend a bit of time figuring out how big a channel you want. And there's no right answer to that because it's going to depend on the resources of the system you're running it on, how much data you're trying to send, how often you're trying to send it. So I couldn't find an automatic answer. The bounded channel helps with performance, but only if you do it right. And if you do it wrong, then you've found a really nasty foot gun. And so I went over to Go, ran a similar test, and discovered that Go has exactly the same issue. And so I felt a little better. But I was still, a little meh on that one. So channel latency. We talked about how long it takes to actually send a message. Well, how long does it take for that message to arrive? So if you've got two threads that are not at all contended, and so into the thread, we send instant now, where it receives the command, we just calculate the elapsed time and indicate the latency for sending that message. Now, it's not going to be the same as the time to send, although it does bring up an interesting question that if you're sending in 80 nanoseconds, but it's taking 160, for example, for your message to get there, how quickly are you going to fill your buffer and run out of memory? So once again, care is required, and that makes the bounded channel a safer option. Well, the answer was that I was a little disappointed by the Rust standard library because it was taking 105 microseconds per message on average. And if I'm sending in 80 nanoseconds, that is an eternity in terms of latency time between my threads. So that's painful. And so that explains some of the problems I was having developing LibreQOS. I went out, I started looking for a few alternatives. And the best one I found was called Canal. We'll get to that in a second. And there's a crazy website called the Rust Channel Benchmarks. If you're interested in this topic, I recommend digging in because they have tested absolutely everything. And one of the things they discovered was that Rust and Go are competitive in terms of speed, but Go has a slight edge. Yeah. How's that? The graphs don't get any easier to read. But we start. So the first thing I noticed here was, Canal here has substantially better numbers everywhere, and so I'm like, okay, what is Canal? But looking at these, okay, so this fellow was sending about 31 million messages per second using the standard library. That's really good. Go on his same system was about 24 million messages per second. Most of the time we're into speeds that you don't need to worry about it because most of the time, unless you're building something utterly crazy like a network monitoring system for 30,000 users, which is what I was doing, you're not going to hit these numbers. But just occasionally, you need to start worrying about it. And so I went to Canal. Canal calls itself the fast sync and async channel that Rust deserves. And then I found some Reddit threads where the guy was talking about what he does, and I couldn't decide if he's absolutely bonkers or really, really, really terrifyingly smart or both, because he is doing some stuff that I wouldn't have even considered doing in a lot of languages. In some cases, he was even experimenting with writing directly to the stack of the receiving thread, which is a supremely dangerous thing to do. If you read the Canal source code, it is full of unsafe and great explanations for how his mad science works. And the amazing thing is that I put it into a beta test of LibreQOS, threw it on the ISP I work for, and it worked flawlessly for 6 months without a single error. So, excuse me, it is a great example of how unsafe code isn't necessarily something to fear. It's something to be really, really careful with. And in his case, be a supremely mad scientist. But what he achieved with it is pretty good. He still got
I'm unfamiliar with this level of the slowness of level. How do you write directly to another function's stack and hand control to it? And yeah, how does that work?
So in his case, when the channel first opens, it basically shares an unsafe pointer to the other end of the channel and tells you that when you have a message, write it here. And so it's not unprecedented. Linux has a system called umem built in for doing exactly the same thing. As packets come out of network cards, they actually blast with DMA directly into a blob of memory and send the kernel ID numbers for which blobs of that memory have been used. When the kernel's done with them, it gives the ID numbers back so the network card can the network driver can write directly into that memory. And Canal basically builds the same thing. It's very, very close to what Van Jacobson initially proposed, because you don't have a locking mechanism other than if the list of places you're allowed to write is empty, then you have to wait until you can write again. But it avoids the need to copy through an intermediary. It minimizes your need for an allocation because you're being told, put this data straight into place. In return, you trade off by having the receiver have to allocate a blob of memory and keep that blob of memory around and promise to behave itself. Because if you were to mess with that memory at the same time as the other threads messing with that memory, then it's anybody's guess what goes on. It is fascinating source code to read. I highly recommend it from an educational point of view. If you're into masochism or just interested, which are honestly one and the same if you've been using Unix for as long as I have. But so going back to Canal, one of the things that really appealed to me is that the syntax for using it is pretty much exactly the same. So when you start looking at Canal code, and I don't have Rust Playground examples for that because Canal isn't on the Rust Playground. But instead of using MPSC sync for a bounded channel, I can just use Canal bounded. And then the semantics for using it are exactly the same. So to rewrite my benchmark programs to use Canal, I had to add one line to my cargo.toml, 0.1 pre-release, which will tell you how far this project has come. And yet, despite that, it's remarkably stable and a great example of just how fast you can go if you really feel the need. The rest of the program is exactly the same. I didn't have to change anything other than creating a Canal channel instead of a standard library channel. Now, in terms of actual time on sending, my results were very similar. And that would make sense because no matter what you're sending to, you're going to be moving that data or copying that data into a destination somewhere. And so for an MPSC channel, I'm moving or copying the data into the channel buffer. For a Canal channel, I'm moving it over to the recipient. But either way, the sending it code isn't that different. The latency on the actual time it takes to get through the channel turned out to be about the same too. And that started to disappoint me. I was like, why is it taking so long to get from point A to point B? And then I did some digging and discovered that that's because the time I'm seeing here is not in fact disastrous. It is the average time for a non-real-time Linux kernel to context switch between threads. And I'm only receiving one message at a time, and then I'm polling to see if there's another one. Linux is letting another thread on that core do something else. I discovered if I pin it to a largely empty core, that latency goes down. So it turns out that's not a Rust problem. That is an operating system problem. So in terms of the sending latency, I discovered it was very, very similar. And so that had me scratching my head. Why is it, that this latency is so poor? So I set up a truly crazy example here where I create 100 threads, each of them with a bounded size of 100 messages. I set it up with some feature flags so I can test it with Canal or with MPSC. And so that literally just replaces the connect function with creating a Canal or a standard library. And then it's the same latency program, except this time I'm going to create 100 threads. I'm going to send the sender into each of them. And then 100,000 times I'm going to blast out messages and measure all of that. And so this took quite a while to compile, so I had to compile and run. So I'm just going to show you some results so as not keep you here all night. But with 100 threads and only one message allowed in the channel, the standard library really starts to struggle. I was looking at 460 microseconds per message in latency with the standard library, and only 61,000 with Canal. So even though you've got massive contention, Canal is handling the contention much, much better. And it's doing that, I discovered, because they completely rewrote their own mutex from scratch and will even fall back to using an inbuilt Linux kernel mutex if it can do so. So I allow 100 messages in to the thread, and now my bounded queue is about the right size. So because of the way the threads are bouncing between each other in the scheduler, there's less contention. So the standard library is catching up, but Canal is still about twice as fast. Start making really big queues, and they're both getting slow. There's a bit of back pressure going on, but Canal is, once again, almost twice as fast as the standard library. But when you start counting messages per second, which is really a factor of both latency and sending time and receiving time, you will find that that's where the 80 times magic 80 times number comes from, because Canal can achieve 80 times better throughput so long as what you're sending is relatively small. What I discovered was if you start trying to send whole giant multi-gig data structures over channels, you're in for a very bad time. But if you put them in a box and you send the pointer to the box, you're in for blazing performance. Usually. And if you've got more than 10,000 threads, then a lot of operating systems will start refusing to make any more. Last I checked, it was 62,000 on Linux. I wrote a test program that made 62,000 threads, and I could no longer log in because it was taking so long switching between contexts. But it was worth a try. So generally speaking, if you start needing a lot more threads, you need to start getting into async, which is the next thing I'm looking at. Most of the time, I recommend trying to have a number of threads close to the number of cores you have. You sometimes want to leave core 0 alone, give the operating system some space to do its thing. I've written game code that used the CPU so efficiently that the operating system never got a chance to finish important jobs like actually loading things. My program was running great, but never received any data from the OS because it never slept. So you need to avoid things like that. 100 threads is not that uncommon if you've got 100 threads that aren't necessarily going to be at 100% CPU usage. It's not that uncommon on a really busy Linux server to see 300 or 400 going at once, but usually not on a single task. But I did, and the standard library keeps up pretty well right up until you start getting contention. And that was also my experience with Crossbeam, was that the Crossbeam threads, the Crossbeam system, there's really no benefit for it until you're overloading your system. All right, so async, which is been getting a lot of bad press lately. I personally use async in professional code every day, and it's really not as painful as people will tell you. But you have to, I teach a whole 3-day class on how to not get a headache with async, so I'm not going to try and go through all of that here. First thing I want to talk about though is that Takio, which is tokenized I/O, is sort of the most common executor runtime for async on Rust right now. You can choose your own backend. There's everything from Guamio, which is Linux only and amazingly fast, all the way down to Small, which is async for microprocessors. Takio is kind of the standard one that I'm just seeing that everybody's using, so I'm using it for most of my examples now. And the big thing I wanted to show you here is that Takio implements its own channels. They're all bounded. You have to specify a size limit, but the syntax is exactly the same. So we've got our command enumeration, just like before. We've got Takio sync NPSC, so it's even with Takio instead of STD, but the rest of the path is the same. Command, we're spawning async with Takio spawn instead of thread spawn. Async move closure. So once again, we're moving the receiver in. Receiver receive, and instead of unwrapping to see if it died, we call await. Now in async land, await is the magic word that means my task is waiting on something else. Let everybody else in the task queue run and wake me up when there's something to do. In this case, the receiver won't be woken up until there's a message for it. So you can have thousands and thousands of these if you want to, and there's almost no CPU penalty for them not doing anything. Obviously, they use CPU when they wake up. So this is exactly the same program with the exception that I stuck a sleep at the end just to make sure that it has time to finish running. It looks exactly like the threaded version from back in slide 4, gives you the same result. Only difference is it's async. We're not spawning new threads. Takio will, by default, spawn 1 thread per core. Each of those will have a list of jobs that it can run. When you run spawn, it makes a new job, picks the CPU. By default, it will try and pick one that you're not currently using to encourage some concurrency. It doesn't have to do that. You can even do this single-threaded if you want and get the same result. It's actually faster too. We'll talk about that in just a second. The reason it's faster though is that quite often you are not crossing thread domains and you're not having to wait for the operating system to schedule for your time to come back. Takio is scheduling you, and there's a tiny, tiny delay between Takio switching tasks. So the big takeaway there is it's exactly the same, with the exception that you await to make it work in async land. And likewise, Canal implements some async version, and they're pretty much the same. In this case, I went ahead and made a mutex to store some latency numbers, just like before. And then instead of, if I use the Canal feature, sorry, not the Canal feature, I use Takio instead of the standard library. With the Canal feature, I spawn Canal's async bounded, which is the asynchronous version of its bounded queue. Then the rest of the program is basically the same. So instead of spawning a thread for the receiver, I spawn an async task. Command's pretty much the same. Figure out the elapsed time, stick it into our list of elapsed times, spawn tasks, which I defined as spawn 100 tasks, each of which will then spawn more Takio processes, which will then in turn send 100,000 messages in through that and give me average latency. And the latencies start to scale quite a bit better because with 100 tasks, we're looking at just 44 microseconds just 44 microseconds when I've even got a bound of 1. So 1 message in at a time, and you have to wait until you can send again. With a queue length of 100, still only 86 microseconds. And this is pretty good because now we've got 100 tasks, each of which is spawning 100,000 messages. We are blasting this poor little channel to death. And so, with a 1,000 messages in the queue, yeah, it's starting to slow down. And Takio is outperforming the standard library a little bit, and that's partly because of lack of context switches. But Canal is still a little faster. So make 1,000 tasks instead of 100. Now, spawning 1,000 threads and having all of them blasting messages in is pretty much performance suicide. My computer barely warmed up its fans with async tasks. That's the joy of an async world. That's big benefit of Go. It's the big benefit of Rust async. It's actually the big benefit of C++ coroutines, which are the same thing too, but is that you aren't spawning heavyweight operating system threads, you're just spawning tasks. You can completely blast the living daylights out of your poor little thing. I actually was benchmarking these on a MacBook Air M1, which is a tiny little system. You'll find on Intel the numbers are actually considerably better. So Takio is better than the standard library in terms of message latency. And when I measured sending time, they were honestly too close to be worth graphing separately. In both cases, you're just waiting a few nanoseconds to send the message and then carrying on your merry way. The Canal can still help you. Crossbeam will not help you because currently there's no Crossbeam async version. But you can start building systems that use an absolute massive number of messages. And if you start looking into web servers like Axum, you'll find out that they are using this really, really heavily, sending messages between subsystems all the time. And I've had 5,000 requests a second running in 20 megs of RAM in Docker in a MacBook Air M1 in a live demo a few weeks ago. And so you can trust this to scale up to what you need. You don't have to worry about it. The channels are not going to be the part that hurts you, but they are going to simplify your program. And so this comes from a question that students ask me all the time. What if I want to be building a system like you find in a lot of corporate systems where some data arrives, bits of it get squirted out to hundreds of different systems, and then you don't know when it's going to die because you don't know which one's going to finish last. So can you start using Arc? And the answer is yes. You can absolutely have a structure of important data, put whatever you want in it. In this case, a couple of integers are obviously vitally important. I added implement drop just to indicate when it will be deleted. Create a couple of channels here for sending important data pointers, which I've defined as being an arc. And an arc is just your data with an atomic number attached to it for a reference count. Whenever you clone it, that reference count goes up. Whenever it falls out of scope, that reference count goes down. And when nobody's looking at it anymore, it ceases to exist. And so Rust doesn't have a garbage collector, except this is a garbage collector. It's just a relatively primitive one. Inside, I'm protecting the data with a mutex. Now, you wouldn't do this in a live important system. You'd actually put some sort of protection for each of your values so that the parts of the program that are working on different parts of the code, of the data, only need to lock the part that they're working on. It's called interior mutability. It's worthy of another talk if you ever want me to give it to you, but it is a great way to handle this pattern. And so you can spawn a thread, receives a message, locks the contents of it, adds one to it, make another thread. We're listening on receiver 2 now. We once again lock it, and we'll add 1 to another value. And so we create my data, arc new, with important data 00, We're going to send it to both threads, sleep, and print the result. And so I printed out the whole mutex here so you can see it's not poisoned, which means nothing bad happened while it was processing the data. We sent the same data off down two different channels for independent processing on different threads. They both worked, and it didn't drop the data until both threads were done with it. It fell out of scope, nothing's looking at it anymore. If you were to use a debugger to trace, you'd find that it never creates a second one because an arc guarantees that there's only one of the contents of that arc. It is shared. If you've used C++, it's the same as a shared pointer. I believe Zig has a similar concept, but I haven't got beyond Hello World with Zig yet, so so it's REST stations and Zig 1 is now? Awesome. So this is a really trivial example, but I just wanted to show you that sticking to the common REST. Oh, I just got a question on the chat. What sort of security vulnerabilities could be introduced by Canal, and is it safe for use in production environments? Well, the answer is I would wait for it to get closer to a 1.0 release before you absolutely bet on it right now. I have been using it pretty heavily in some open source projects where it's not the end of the world if there's a failure. And I have yet to have a situation where Canal has caused me a long night or a stomachache. So far it's been very, very good. But you shouldn't take my word for it. I would recommend letting it mature a little bit, get a little further before you start betting the farm on it. But because it's so close to the standard library one, I would use the standard library one. If the channel turns out to be your performance problem, Canal is where you can go to look for an answer. As for what sort of security vulnerabilities, the answer is honestly kind of limited. Because when I look through their code, they've been very, very careful. They're not getting rid of things like bounds checking or all of the other things that help Rust remain pretty safe. Mostly the unsafe code is copying data from one pointer to another. Theoretically, if you could find a way to make that data exceed what's being bounds checked, you could smash the stack on the other end, but I couldn't find any way to do that because it checks the size before it sends it and receives the size of where it can send it to. And so it seems like even though it's unsafe code, they're following safety protocols pretty well. They're just being very, very clever and doing things that you can't really express in safe Rust. Does that answer your question? Oh, and Jay's muted, so I don't know if that was a yes or a no. That was Jay in the Zoom chat. Oh, Jay is more concerned by the resume of the author, and I would agree with that. And I honestly don't know either. I've just been impressed by the code I've seen. I thought I'd bring it up to show you just how much options you have. I'm definitely not saying go ahead and bet the farm on it now, but be excited because this is a lot of important people are looking at what he's doing here, and I really think this is going to turn into something special pretty soon. Okay. Okay. So anyway, the takeaway for the fan-out processing slide is that if you have data that you need to send to lots of different places and lifetimes become muddy, ARC is your escape hatch from lifetimes because it adds reference counting. You don't go read the Learn Rust with altogether too many linked lists tutorial. It will terrify you. ARC has various escape hatches. It's exactly the same as shared pointer in C++ and the equivalent in other languages. You can create cycles and things with it, but you kind of have to try. If you run into that problem, there are answers out there. generally speaking, Arc adds 100 to 150 nanoseconds on a modern Intel CPU of latency for accessing that atomic reference counter. You don't have, it's not going to kill your performance. Use interior mutability to lock the parts that you're working on in different places. You can make a really high performance, well-divided program. So different groups of you can work on processing different parts of whatever very important data happens to be. And also, it's a really good idea to have something that fires when that data goes away, because it's not always clear when you work on, and the drop method is what I use for that. I sometimes attach a save mechanism to the drop method on important data that's going to be processed by 10 different services. The reason for that is I don't know which service is going to finish first. I want to ensure that what I'm saving is when all of them are done with it. And so that drop mechanism allows me to say, hey, it's going away, they're done with it. Or I can start accumulating messages saying, service 1 is done, service 2 is done. That gets messy. Sometimes just saving on drop is a great idea. Last thing I'm going to talk about, just because it comes up quite a lot as well. RESTConf in particular, I kept hearing the comment that the async people and the threaded people don't talk to each other. And I just want to promise you that that's not true. In fact, they're many of the same people, because the Rust core team really isn't that big. And there's been a lot of effort to make sure that even though you can't run async code without an active async runtime, there's plenty of options to mix and match threads and async in your program. A good example of that is if you wanted to use async for one core maybe that's just handling network communication with other servers in your system, and then you want to use all your other cores for heavy CPU-bound threads, you can do that. And so this is a quick example of where in an async program, so I make an async thread using Takio, but I also make a synchronous thread using the standard library. And then I use thread spawn to create a thread, print that I received a message on the synchronous receive channel, so the threaded receiver. And then the async channels include a function called blocking send that allows you, if you've got a sender for that, even though you're not in async code, you can call blocking send to send data into the async context and have something work on it there. So this is kind of a why peanut butter or chocolate when you can have both. It's very easy to mix and match the two. So we then spawn a Takio task that listens on the async receiver and just indicates it received an async message. Now, because async can always call into synchronous code, you don't need to do any sort of magic or a dance to call into the thread-based channel. You do have to use a little bit of magic to send into the asynchronous channel. Just to prove if it works, we send 42, life, the universe, and everything into the threaded channel. And we sleep to make sure that we have time, that the program doesn't terminate before we get a result. And the playground actually just went down on me. I can run this in VS Code if it doesn't work a second time. Yep. Here it is. All right. Is that big enough for you guys? It's the same source code we were looking at a moment ago. I ran it. As you can see, it receives the message. So it sends it into the thread. The thread received the message, sends it back into the async context, and the async task receives the message. And so the big message there is, one, don't rely on the Rust playground for live demonstrations. Compile and run it locally. And more importantly, threads and async don't have to be separate citizens that never talk to each other. They actually work best together. If you want to really take advantage of them in something big and complicated, you quite often want to mix and match some of the best elements of both. You might have part of your program that runs best with async tasks and part that really needs to pound the CPU and needs threads. Don't be afraid, and channels give you an easy way to talk between the two of them. All right, so that is the end of my presentation. Don't know if any of you guys have any more questions, but I am all yours. Uh-huh.
Is it blocking? Is it blocking just the thread for the sender? Could it also block the thread for the receiver if it happens to be scheduled on the same core? Like where is that blocking?
Okay, so I probably should talk about this. There's a little bit of terminology here. That whenever you run async context like Tokyo or small, these standard is to refer to launching the async context with a function called block on, which sounds like a bad aerosmith sign, but what it means is block on these asynchronous programs, asynchronous functions, and keep blocking until it's done. And in this case, it's the same thing. The channel doesn't block. The Tokyo receiver doesn't block. But your thread program will block for however long it takes, typically 80 to 100 nanoseconds, for that message to be injected into the async context and sent with the thread. So blocking send is really a short handle for take the current Tokyo runtime and spawn a send on this channel inside the current runtime. Does that make sense?
I'm trying to remember the things that are not blocked.
Okay, so typically when you in the async world, when you refer to awaiting, you're not blocking because you're encouraging something else to run. And so the async world tends to use the word blocking kind of differently to the threaded world. Another example of they should have lunch together more often. So in the threaded world, when you block, it means you tell the kernel, I'm busy, come back to me later. And you're not doing that. You're more like an async block where you're saying, okay, I'm going to not let anything else use my thread until I finish sending this message, which fortunately is usually a very fast operation, but it's honestly poorly named. I would have named it send into async.
Okay, I think that's making more sense now. Thank you.
You're welcome. Okay.
Can you hear me?
Badly. Let me turn my volume up. I love this day and age. I actually have Bluetooth synced straight into my hearing aid.
That's so cool.
Excuse me, yeah, so I was in a college class where we were doing distributed systems, and we were implementing Raft in Go, which does replication of data messages. Basically, as I was doing it, I really didn't want to use mutexes if I could help it. And I was like, I'm going to do this with channels. I'm going to be clean and pristine in all of my code. And it turned out that it was really hard to make it work properly with all of the synchronization with just channels. It turned out we needed mutexes to make it work, at least within the context of the class. So I'm just wondering, from your perspective, is there anything that can't be done with channels that you're like, well, I think I really do need to fall back here on mutexes?
So if I have a giant blob of shared data that lots of things are updating, and one or two things are actually accessing, I will most likely just go with a shared data structure. probably using something like dash map so that I don't have to worry about locking and unlocking. It's a lock-free deterministic speed hash map. Basically, it's a wonderful structure. So in a case like that where I've got maybe multiple threads writing who knows where into the structure at any given time, and I'm just interested in reading some results at some point or maybe periodically, then no, I would not use channels. I'd use a shared structure. I prefer channels for a more pipeline type approach where I want some data to arrive, send it to the next logical location, send it to the next logical location. In fact, I often tell people who are getting started that if you really want to pretend you have microservices, use a channel instead of making a network call for every connection between them. Your performance won't suck, and you won't have the absolute misery of trying to figure out Kubernetes before you have your second customer.
That's fine.
And I wanted to add on to what you're saying there, which I think you're kind of saying the same thing. The Go proverb says, channels orchestrate, mutexes serialize. So I think that's kind of a...
That's about right. Now, Rust lets you cheat a bit by having interior, you can have multiple mutexes inside one structure. I think you can do that with Go too, actually. So you can be serializing different parts of the same structure, and you can do it safely. Rust will even tell you if you've done it wrong. So sometimes it's less true, but a lot of the time it is. A mutex is like a stoplight. Everybody has to stop until it's their turn. Whereas a channel still serializes in a way because everything goes into the channel and the messages do arrive one at a time.
Yeah. Thank you.
You're welcome.
This is a terrible idea. You can implement mutexes with channels.
Yes.
Yes, you can.
So technically it would be possible.
Yes. In our case, there was like a lot of things that needed to happen within the same mutex lock. So I think that Go proverb was apt because it was like, okay, at this point of the program, these things must happen serially. They cannot happen asynchronously. And so we need to lock from here to here in order for it to work. And then there just wasn't a clear way to express that with like passing something along a channel or even using an atomic data structure. It was just kind of like, we need to do these procedural steps in a serial manner. So yeah, all these tools kind of, it's very clear what they're used for.
Yeah, probably in a case like that, I'd say step back also and do the tasks together inside a mutex lock. Where the channel would probably be useful would be to tell you that you need to do those steps, if that makes sense. So so one step of the program saying, "Hey, I'm done. Module B, do your thing." One of the guys I work with at Ardan Labs, Bill, is always saying, "Be nice to the machine." And if you sit through his training, you'll hear that probably 100 times a day. So you'll want to strangle him, but there's a good message there behind it. That a lot of the time, even though we've got these amazing CPUs that can do a million things at once, and sometimes a lot of the battle is actually getting them to do them in the right order. And so, unfortunately, Rust gives you fearless concurrency, but it also gives you the ability to fearlessly do something really stupid while you shout Leroy Jenkins. So you do need to worry about that a lot.
All right, do we have any other questions? Or shall we adjourn the presentation portion and continue on to the merriment?
Did smoke come out at any point during those tests in your computer? Sounds like a lot.
No. No, I actually, I have a 1-year-old, nearly 2-year-old daughter who's been homesick for about a week, and I was running those on my MacBook Air in bed, and I wasn't heating up the sheets or anything, so trying desperately to be silent so as to not wake up her super hearing.
All right. Well, thank you again for joining us. This was an excellent presentation, a banger way to end the year. So thank you so much. I learned a lot, and it seems like everybody else did too, or at least some people. I don't want to speak for everyone's intelligence, but I think that there was a lot of learning in the room. So greatly appreciated. Excellent preparation. Thank you so much.
Cool. And thank you for having me.
All right, I'm going to go ahead and disconnect the stream here, and then we are going to continue on with our hanging out. All right? Have a good one.
You too. You too.
Thank you.
Thank you.
Bye, Herbert.
Thank you.
Thank you. Thank you.
All right, and then I'm going to stop the stream. I have just a few orders of business